Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, for the full hour, we're going to be talking about origins, the origin of the universe and the origin of the human race. Now, of course, we live in a free country. Everyone's allowed to say whatever they believe. However, science has a responsibility. Science is based on reproducible experiments. Experiments that can be done anytime, any place in the laboratory. And of course, we all have ideas about perhaps where humanity came from and where the stars came from. But science has reproducible evidence that the universe came from a cosmic explosion 13.7 billion years ago called the Big Bang. And humanity evolved on the planet Earth via mutations in our DNA. As a consequence, we have two very special guests for you today. The first special guest is Simon Singh. He was trained as a physicist. He's a BBC commentator, and he's hosted a number of science specials for BBC, and his latest book is called The Big Bang. So today, we're going to be talking about the fact that the Big Bang Theory is experimentally verifiable. In fact, radiation from the Big Bang is still circulating around the universe even as we speak, and you can actually pick it up with our instruments. In fact, if you turn on your radio and you hear static between the radio stations, about 15-20% of that static actually comes from the Big Bang itself. So in other words, the cosmic background radiation in the microwave region actually can be picked up by our TV sets, by our radios, and by the Internet. All of it is vindication of the Big Bang Theory, as we'll see with the interview with Simon Singh. And then in the second half of Exploration, we're going to talk about the origin of humanity. We should also point out that Charles Darwin was born in 1809. He published his seminal work in 1859. So we just passed the 200th anniversary of his birth and the 150th anniversary of the publication of Origin of Species, which set off a firestorm of controversy. And in the second half of Exploration, we're going to bring on Dr. Spencer Wells. He's a biologist, and he's also a commentator for the National Geographic TV program concerning the origin of humanity. Do you know that we can actually trace back the origin of ancient migrations that have long been forgotten all the way back to Africa? In fact, for a BBC special that I hosted on the nature of time, I had my own DNA read. Blood and saliva samples were taken from me, sent to Vanderbilt University and also Cambridge University, and scientists were able to decipher my lineage going back several tens of thousands of years. In fact, 4 of my genes were very carefully cataloged in this study, and there's a data bank of about 20,000 people who also donated blood and saliva samples and had their 4 genes read. And then on a map of the Earth, I could see the precise correlation of who on the planet Earth had precisely the same 4 genes that I had. And bingo, you could see where your ancestors came from, and you can also trace out the vague migratory path that your ancestors took. And of course, all these paths eventually lead to Africa, because we left Africa roughly 50,000 years ago. So modern humans, as we now know, evolved out of Africa roughly 100,000 years ago. Then several migrations began to emerge from Africa, one large migration about 50,000 years ago, and then that migration in turn split into many other pieces. One piece went into Eurasia, and these people became the Asian people and also the Native American people. Another branch split off into Europe, creating the Europeans, and smaller branches spread out and basically colonized the entire Earth. Unfortunately, we have lost all ancestral memory of this great diaspora because it took place 50,000 years ago, and writing is only roughly 5,000 or so years old. So in other words, in the second half of the program, we'll be bringing on Dr. Spencer Wells, who'll be talking to us about how we use genetics to trace the origin of humanity and the ancient migrations back to Africa 50 to 100,000 years ago. So once again, our first special guest is Simon Singh, talking about the Big Bang, his latest book, and he is a science commentator for BBC television. Dr. Singh, let me first ask you about one of the greatest paradoxes in all of cosmology, which is Olber's paradox. Olber's paradox says that if the universe is infinite, has no beginning, no end, and is uniform, then there should be an infinite number of stars in the sky, an infinite amount of light entering your eyeball, and therefore the sky should be on fire. The night sky should be white, not black, because everywhere you look, you're staring at an infinite number of stars. So how do we resolve this Olber's paradox, the fact that the night sky should be white with an infinite number of stars, but actually is black?
Yes, I think it was a real problem. As you say, it's a nice piece of mathematics. You can sort of just look at shells of the universe, and every shell contains a finite number of stars, and if you build up the shells, it turns out that wherever you look, you should see a star. And therefore, the night sky, as you say, instead of being pretty much black, would be pretty much brilliant white, infinitely bright. And I think astronomers were fundamentally stumped by this. So I think you can come up with all sorts of ad hoc excuses. You know, maybe there's dust in the universe that absorbs the light. Well, then the dust should re-emit the light. Can't get rid of it. You know, people tried to come up with all sorts of excuses, but none of them were really very satisfactory. If the universe is eternal and pretty much unchanging, there's no real way out of Olber's paradox, I think.
So it was Edgar Allan Poe, according to historians who've gone through the record, it was Edgar Allan Poe, the famous American mystery writer, who practically on his deathbed wrote the solution to Olber's paradox. So maybe the universe had a beginning. Maybe there's a cutoff with regards to the amount of light that hits your eyeball when you look in outer space. Well, could you elaborate?
Yeah. I mean, I didn't realize that Edgar Allan Poe had sort of come up with this first, but as you say, the way we now get out of Olber's paradox is with the Big Bang Theory. The Big Bang Theory says the universe hasn't been here forever. It's only been here for a finite time. We now know that's roughly 14 billion years. The best guess we have is 13.7 billion years. If the universe has only been here for a finite amount of time, then light can have reached us only from a finite volume of the universe. So out there, way, way, way beyond this kind of horizon, there may be tons and tons of light, but none of it's reached us yet because it's too far away. So we effectively live in a sort of a finite volume of observation, and therefore we only see a finite amount of light. And I think that's how we get out of Olber's paradox today. In other words, you have to abandon the idea of an eternal, infinite universe and embrace the idea of a universe with a finite age that was actually created a finite time ago.
So it's rather amazing that the reason why the night sky is black is because there is a cutoff, as Edgar Allan Poe mentioned in his book. There's a cutoff. Light hasn't had time to reach us because there was a beginning. Now, the Hubble Space Telescope has actually given us photographs of the most distant stars in the universe. And sure enough, when you go past the most distant stars, there is blackness. There is essentially the Big Bang. The Big Bang is essentially staring at you in the face. And, of course, the Big Bang you cannot see because it's in the microwave region. But that's the reason why the night sky is black, because you're literally staring at the Big Bang.
Yeah, it's very interesting that if we go back 100 years, you know, Einstein was sort of his 100th anniversary of his Annus Mirabilis. If we go back to 1905, pretty much the whole scientific establishment thinks that the universe has been here forever. They don't believe in the Big Bang. And yet, in a way, the clue was there. Olber's paradox is what should have been telling them that they have to really move towards a Big Bang model. And Edgar Allan Poe, that's interesting to know that he sort of first posited this. One of the first people to sort of posit it in a more mathematical framework was the Belgian cosmologist Georges Lemaitre. in around 1927. And he sat down and wrote down the equations and said, look, logically, it is possible, if we look at Einstein's theory of gravitation, that everything is consistent with the idea of a Big Bang universe. He didn't talk about a Big Bang. He used phrases like a day without a yesterday. But essentially, he was solving Olber's paradox by saying the universe started with a Big Bang. Still, nobody believed him, though. Still, the scientific establishment wanted to hold on to its notion of an eternal universe. Like every establishment, people are sort of comfortable with what they know, and they're reluctant to embrace new ideas, especially as there wasn't really much observational evidence to back up Lemaitre's idea. So the Big Bang in the mid-1920s was very much a hypothesis.
Okay, now let's go to the late 1920s, where we have Edwin Hubble, who is perhaps the greatest astronomer of the last century, where we have the discovery of the expanding universe from Mount Wilson Observatory in California. So could you elaborate now, what did Edwin Hubble find? Well,
Hubble looked up into the night sky and studied galaxies and was measuring what we call redshift. If you listen to a car go by at high speed, it makes that classic noise, it goes from a high pitch to a low pitch. As it approaches, the sound waves are sort of compressed. As it leaves, the sound waves are drawn apart. Now, if a galaxy is approaching, it doesn't make a sound, but the light waves are sort of compressed. The physics is a bit more complicated than this, but essentially, if a galaxy is coming towards you, it should look a little bit blue. If it's moving away from you, it should look a little bit red. Now, whenever Hubble looked at a distant galaxy, it was always red. It was always red-shifted, always redder than it should have been. So if all the galaxies in the universe, all the distant galaxies, if they're all red-shifted, they're all moving away. If they're all moving away, well, that's exactly what you would expect if the universe started with a Big Bang. Hot, dense, compact object explodes outwards. The debris forms galaxies. The galaxies should still be flying apart. And that's exactly what Hubble was seeing. So this is sort of 1929 to 1931 when this data sort of started rolling in. It was the first real evidence to sort of indicate that maybe Lemaitre was right. Still, the scientific establishment didn't embrace the Big Bang theory. It's like building a case in a court of law. You don't convict somebody on maybe just one piece of evidence. If the Big Bang is guilty of creating the universe, we want more than just one piece of evidence. So Lemaitre and the other supporters of the Big Bang theory had to continue their battle to find proof of the Big Bang. But Hubble's data, you're absolutely right, was pivotal in beginning to swing the debate in their favor.
Okay, now let's go to the 1950s when a British astronomer and his colleagues, led by Fred Hoyle, begin to challenge the Big Bang theory. And apparently, in a BBC debate with George Gamow, Fred Hoyle coins the word Big Bang as a rather derisive comment. After all, it wasn't very big, and there was no bang. But tell us a little bit about the debate between Fred Hoyle and George Gamow.
Well, yeah, I think Gamow was a proponent of the Big Bang theory, whereas Hoyle was very skeptical. And I've heard this BBC radio piece of archive, and it's lovely to hear Fred Hoyle in his very kind of Yorkshire, abrupt, down-to-earth voice saying, he says, this Big Bang theory to me seems unreasonable. And he used the phrase as an insult, Big Bang, just kind of a throwaway comment. But the name stuck. And critics liked it, the fans liked it, and we've sort of used it ever since. But the reason that Hoyle found Big Bang to be unreasonable was he just found it, I think, philosophically unpalatable to have eternity, to have a creation. He didn't like the idea of a moment of creation. To me, it sort of smacked, to him, it sort of smacked of a god. But on the other hand, he had to accept that the universe was expanding. The universe was getting bigger. So how do you marry those two things? The universe that is changing, but on the other hand, Hoyle wanted it to last forever and to have been here forever. And his way to sort of marry those two ideas was to say, okay, the galaxies move apart because the universe is expanding. But then new matter is created in the gaps. And that new matter evolves into galaxies. And then that galaxy moves away, and then a new galaxy is born. And so that way, the overall density of galaxies in the universe remains the same. If you look way into the future, the overall galaxies remain equally dense. If you look way into the past, the number of galaxies per certain volume remains the same. And this was called the steady state theory of the universe. My understanding was that I met Thomas Gold, who worked with Fred Hoyle on this, and he told me a story that they went to see a film in 1945. And the film is about a young man who wakes up one morning. He's had been having a huge dream, a very vivid dream. In the middle of the dream, he suddenly wakes up. He gets washed, he gets dressed, he jumps into his car, he drives into the countryside, his car breaks down, goes into a house looking for help. Things go horribly wrong. It's a sort of slightly drawn-out story, but things go horribly wrong. And eventually the people in the house grab the young man and strangle him. They throttle him. And just as they're about to strangle him to death, he wakes up. He's been having a dream. He gets washed, he gets dressed, he jumps into his car, he drives into the countryside, his car breaks down, he goes to a house, he looks for help, and so on and so on. So here's a film that has a sort of cyclic or continual version. The film could go on forever and ever and ever. It sort of develops, but it sort of stays the same. And it was seeing that film that inspired Fred Hoyle and his colleagues to develop their steady-state view of the universe, a universe that clearly changes because it expands, but one that sort of could stay the same.
Now, the Big Bang Theory did have a flaw, and even George Gamow admitted this. If the Big Bang was very hot, it was an oven. And if it was an oven, it cooked the higher elements. And so all the elements we see around us, carbon, oxygen, nitrogen, should have been cooked in the furnace of the Big Bang. But the data didn't seem to fit. It seemed to explain the abundance of helium quite nicely, but it didn't explain the abundance of the other elements. So how was this flaw eventually resolved?
Yes, it's possible to do quite detailed calculations about the early universe. If you go back to a few minutes after the Big Bang, you know the density of particles, you know the temperature of the Big Bang, and you can work out exactly what cooking should have gone on. And what you can't do is cook the heavy elements, gold, platinum, sodium. They're just too heavy to have been cooked in this short window of what's called nucleosynthesis. And this was an embarrassment for the Big Bang because the Big Bang was supposed to account for everything. Now, ironically, Fred Hoyle, who hated the Big Bang, helped the Big Bang get out of this hole. What Fred Hoyle, working with Willie Fowler and Margaret and Jeffrey Burbidge, together they wrote an incredible paper called B squared FH, Burbidge, Fowler, and Hoyle, after the names of the authors. In this paper, they explain that if you have different stars of different masses at different points in their lives, at different generations, when those stars collapse, depending on their makeup, they create the heavy elements. And depending on their background, they create different elements. And so it's the collapsing, the death of stars that create the gold, the platinum, the sodium, and everything else. So the story we have now is the Big Bang creates hydrogen and helium and a few others, the very light elements. That goes on to form the stars, and then the stars form the rest of the periodic table. And so even though Fred Hoyle was a great critic of the Big Bang, one, he named it, as we said earlier, and two, he helped the Big Bang through the process of stellar death to create all the elements around it.
Now, what finally killed the steady-state theory was the discovery that the afterglow, the shock wave, the echo of the Big Bang is still reverberating throughout the universe, and it could actually be observed experimentally. It was predicted by George Gamow in 1948 with his students, and then found in the 1960s. So explain to us the cosmic microwave background radiation.
Predicted is the key thing here. I think 1948, Gamow, Robert Herman, Ralph Alpher sat down and made a make-or-break prediction. They said if there was a Big Bang, and in 1948 not many people believed in the Big Bang, but they said if there was a Big Bang, it should have been followed by a blast of radiation. What they meant was that in the early universe, all the light, the radiation would have been trapped by sort of scattering off all the charged particles. But after about 400,000 years, those charged particles couple up and form atoms. And suddenly this radiation is released to stream throughout the universe. And as the universe is expanding, this radiation would sort of get stretched. And now today, we should see that radiation in the form of microwaves, the cosmic microwave background radiation, if the Big Bang Theory is true. Look for those microwaves. If you find them, you know the Big Bang Theory is true. If you don't find them, you know the Big Bang Theory is wrong. So make or break test. They were really putting the neck of the Big Bang on the line. And in 1948, nobody could really test this prediction because people didn't have the technology to pick up such microwaves supposedly coming from outer space. But in 1965, Arno Penzias and Robert Wilson, working at Bell Laboratories in New Jersey, had a radio telescope. They were radio astronomers. You pointed up at the sky. You study the radio waves from galaxies. And that way you can work out what's going on inside a galaxy. But even when they didn't point it at a radio galaxy, in fact, when they were trying to calibrate it by pointing it away from a radio galaxy, they still got microwaves. Microwaves are a type of radio wave. They pointed it in a different direction. They still got microwaves. They waited 24 hours. They still got microwaves. Whatever, wherever, whenever they pointed their telescope, they got microwaves. And to start with, they blamed it on a couple of pigeons that were in the telescope. But nothing to do with the pigeons, nothing to do with anything else. Eventually, they realized the microwaves were real. They were coming from the Big Bang. In fact, a cosmologist had to point it out to them and say, look, what you've discovered is the echo from the Big Bang, a kind of luminous echo, an afterglow of creation. The wavelength of these microwaves was exactly what you would expect if it came from the Big Bang. And this is 1965, and it really was a pivotal moment in the history of the Big Bang, because suddenly a lot of people who'd previously been skeptical changed to the other side. So Herman Bondi, who recently passed away, had been a huge supporter of Fred Hoyle. But he'd always said, look, show me one fossil that the Big Bang happened, and I'll believe you. Well, here was a fossil radiation left over from the Big Bang. And, in fact, if people tune their radios in between stations and they hear that hissing, crackling sound, 1 or 2% of the energy that their aerial is picking up is this energy from the Big Bang.
Now, do you find it rather scandalous that George Gamow and his colleagues never won the Nobel Prize for one of the greatest predictions of the last 100 years, and that Fred Hoyle never won the Nobel Prize for nucleosynthesis, even though his colleagues won the Nobel Prize? Do you find that rather scandalous?
Yes, I think Fred Hoyle's case, I think, is particularly sad because, he was wrong about the Big Bang, completely and utterly wrong. But on the other hand, he was incredibly intelligent, a brilliant cosmologist who made great breakthroughs in many areas. And I think he certainly deserved the Nobel Prize for his work with Willie Fowler and the Burbages. Fowler did get the Nobel Prize, Hoyle didn't. And maybe the reason is that Hoyle was very outspoken. He said it how it was, and this often offended people. So when Jocelyn Bell Burnell was overlooked for a Nobel Prize, he openly criticized the Nobel Committee. Later, towards the end of his career, he had some rather crazy ideas. In fact, Hoyle came up with lots of crazy ideas. Some of them turned out to be true, but a lot of them didn't, and those that didn't somehow tarnished his reputation. In terms of Gamow, Alpha, and Herman not getting a Nobel Prize, I think that's a great shame too. It's one of those limitations of the Nobel is that only 3 people get the Nobel Prize. So you've got 5 people here. You've got Gamow, Herman, Alpha, and then you've got Penzias and Wilson. Who gets it? Who doesn't? Who's on the list? Who's off the list? That's a kind of arbitrary decision. Some people say, Wilson and Penzias weren't even looking for the Big Bang. Why should they get the Nobel Prize for making such a lucky discovery? Their discovery was pure serendipity. I think they did deserve credit for their work because many people probably detected that microwave radiation, but they ignored it. because it's so gentle, so light, that you can pretty much do your experiment anyway. But Penzias and Wilson refused to just ignore it. They wanted to get to the bottom of it. And so they were really good observational astronomers. And just for their tenacity and determination and attention to detail, as well as their luck, they deserve the Nobel Prize.
Now, earlier we mentioned that Einstein introduced a fudge factor in order to stabilize his universe to account for the Bentley paradox of a collapsing universe if gravity is attractive. But now perhaps Einstein has the last word, because now the recent data seems to indicate that the universe is expanding out of control, and it will eventually die in a big freeze, all because of this cosmological constant, which we now think dominates the entire matter-energy content of the universe, making up 73% of the matter-energy content of the universe. Could you elaborate?
Yes, I think so. Einstein, first of all, didn't have a cosmological constant because his equation was beautiful without it. Then he added it in to stop the universe from collapsing. Then when the Big Bang theory was sort of shown to be right, he threw away the cosmological constant, calling it the biggest blunder of his life. And remember, the cosmological constant seems to repel the universe, it seems to drive it apart, a sort of anti-gravity. And now, I mean, when I was an undergraduate, I was taught that gravity should be pulling the universe back, slowing down the expansion, maybe even causing the universe to collapse. When people tried to measure this in 1998, what they found is that the universe is not slowing down. If anything, it's expanding faster and faster and faster. There seems to be some kind of anti-gravity pushing the universe apart. And that is exactly what Einstein's cosmological constant would do. So first of all, it was out of fashion, then it was in fashion, then it was out of fashion, now it's back in fashion because it seems to explain these anomalous results. And it's a very new discovery, the observation of this accelerating universe. And so cosmologists are still coming to terms with it. But at the moment, it has the label dark energy. And at the moment, the best explanation is that it's the cosmological constant that's causing this runaway expansion.
Well, I'm afraid that's it for the first part of Exploration. In the second half of Exploration, we're going to bring on Dr. Spencer Wells, hosting a National Geographic special about the origin of the human race. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is the second half of Exploration. In the first half of Exploration, we talked about the origin of the universe with Simon Singh, author of the book The Big Bang and commentator for BBC Television. And in the second half of Exploration, we're going to talk about the origin of humanity. You know, where science and religion seem to be most sharply pitted against each other is on the question of origins, because we are talking about the fact that a small minority of religious fundamentalists are on the rampage against evolutionary theory and also the Big Bang theory, both theories they wish to ban from the textbooks. However, science is different from an emotional diatribe. Science is based on reproducible experimental evidence. We have hundreds of data points, all of which point to the Big Bang theory. If one data point were out of place, we would have to abandon the Big Bang theory, but all the data points are right in sync. Same thing with evolutionary theory. And in fact, this year and next year are quite remarkable in the history of biology. We're marking the 100th anniversary of the publication of Origin of Species by Charles Darwin and the 150th anniversary of his birth. So this year and next year mark a very special date on the calendar of any evolutionary biologist. So our special guest in the second half of Exploration is Dr. Spencer Wells. He's a biologist and also commentator with National Geographic Television, and he has hosted a special concerning tracing the origins of the human race going back 50,000 years. And now I'd like to introduce our special guest today. We're very delighted to have with us Spencer Wells. He's a geneticist with National Geographic, and he made headlines recently by tracing the Y chromosome. The Y chromosome is handed down from father to son, and thereby looking for mutations within the Y chromosome through populations of the Earth, you can actually trace the lineage of humanity. That's right. So today we're going to talk about the origins of the human race over the past 50,000 years. So once again, our special guest today is Spencer Wells. We are talking about the Y chromosome and the ability of geneticists to recreate the family tree of humans over the last 50,000 years. The first question for you is, how did you first get interested as a youth in the whole question of biology?
Well, it came about kind of secondarily. When I was very young, kind of 6, 7, 8 years old, beginning to think about how I want to spend the rest of my life, to the extent that you can at that age, I was fascinated by history, by the idea of traveling back in time. I went to see the King Tut exhibit that toured the States in the late 70s. And was absolutely fascinated by the idea that, there was a culture that existed thousands of years ago, and they made these amazing things. So it was, from a historical background that I was interested in, investigating the world and all of that. And around that time, my mother actually went back to school to get her PhD in biology, and I started hanging out in the laboratory with her, and I discovered that science, while, it is kind of odd in some ways, it's not really about, secretive people speaking a special language, wearing white coats. It's really about discovering new things. It's about creating novelty. And every day is like solving a puzzle. And that is an incredible thing to be able to do. And so, I started off with this interest in history, but it kind of morphed into a love of what you can do with science, investigating the world and discovering new things. And ultimately, by the time I was in high school, I decided that I wanted to use science as a tool for investigating the past, and that's what I've ended up doing, so I'm very lucky.
And how did you get interested in the whole aspect of using genes to trace human genealogy going back thousands of years?
Well, if you are scientifically minded and you want to be a scientist, there's a lot of mechanistic stuff that you need to learn. You need to learn how atoms combine into molecules in organic chemistry, and you need to learn how genes are turned on and off and all of that stuff. But again, what I wanted to do ultimately was to use the knowledge of biology, use molecular biology as a tool to investigate the past. And so as a biologist, that means that you're studying evolution. You're studying the biological history of a species. And I did my PhD work with a guy called Dick Lewontin, a very famous genetics professor at Harvard, working on fruit fly evolution. And you find out, if you investigate the way genes change over time, the way evolution actually occurs at a mechanistic level, that so much of evolution has to do with population history, the history of how individuals and populations have moved around and mated with each other. And that's just not inherently interesting for fruit flies, at least for me. Mm-hmm. But it is when you kind of map it onto human history and you start thinking about human migrations and human origins, and that's where I really made the switch. I started using these techniques that we had developed over many years for studying species evolution, and wanted to apply that to studying questions of human history and, where did we originate as a species? How did we move around the planet? How did we get to Tierra del Fuego in Iceland and places like that? So using the tools of genetics to study the past.
Now, last year we had Professor Sykes on the radio show. He traced the lineage through the female genome, looking at the genes within the mitochondria of the cell. And he even dubbed certain names. Laura, for example, was the woman
whose children, believe it or not, or whose genes have spread to all Europeans and Asians. And he gave a rather graphic account of how you can trace the genes to the female line. Now, you've done a lot of work on the Y chromosome. So tell us a little bit about what is the Y chromosome and why is the Y chromosome so crucial in terms of unlocking the genealogy of human evolution?
Well, if you can trace back in time through the female line to find an Eve, it begs the question of, was there an Adam around at the same time? Is there a tool that you can use to study the male line of descent? And it turns out, yes, there is, and it's what we call the Y chromosome. Now, sex in mammals is determined by the sex chromosomes. And if you have mismatched sex chromosomes, an X and a Y chromosome in this case, you are a male. If you have two X's, you're a female. So this is a chromosome which doesn't actually do very much other than to make men men. But because it is mismatched with its partner, the X chromosome, it doesn't go through the recombinational shuffling that occurs in most of the genome every generation, something that mixes up the genetic variation and creates new combinations, which is probably a good thing evolutionarily, which is the reason we have it. But it makes our lives very, very difficult. So for studying migration patterns, human origins, and so on, we ideally want a piece of DNA that isn't shuffled because it mixes up this variation, makes it very difficult to follow the order of events, if you will, going back in time. So we tend to study these non-recombining pieces of DNA, and Professor Sykes talked about the mitochondrial DNA tracing this female line, and we have studied the male line, the Y chromosome, which again does not recombine. It turns out that it is a fantastic tool for studying human migration patterns for lots of reasons. The main reason is human mating patterns in most indigenous groups over time follow a particular rule, which is that the men really determine group membership, and therefore their Y chromosomes tend to stay put. Oddly enough, in most indigenous populations, the women tend to move around more than the men. And so the signal, the genetic signal that distinguishes between populations tends to get blurred much more rapidly for the female line. That makes the Y chromosome a much better tool for studying differences between populations and therefore the migratory routes that we followed. So in trying to find this kind of Adam lineage, it turned out that we also identified a tool which is fantastic for following migratory routes, which is what we want to be able to do, to reconstruct these journeys we've taken around the world.
So if you were a man, it means you have the Y chromosome of your father, your grandfather, your great-grandfather, but mutations occur along if you go back far enough, and I guess by tracing the sequence of mutations, you could then trace the family tree, right?
That's right. DNA is a very, very long molecule, and although our cellular machinery is very good at copying it when we have children, occasionally we make a mistake, a little spelling error, a single letter change, typically, in the DNA sequence, and when those changes are passed on, they create a line of descent. If you share a change with someone, you must share an ancestor at some point in the past. And so it's these changes that have accumulated over time that we use as the tools for studying the past with DNA.
Okay, now let's go back chronologically concerning the evolution of modern humans and migration patterns. Many anthropologists believe that about 100,000 years ago, plus or minus tens of thousands of years, but about 100,000 years ago, modern humans who look pretty much like us, you give them a haircut, a three-piece suit, and put them on Wall Street, and they look like pretty much all the other barbarians on Wall Street. So let's say you now trace the lineage, because at that point an out-of-Africa thing happened. Migrations took place out of Africa of modern humans. So now trace for us what happens 100,000 years ago as humans began to leave Africa.
Well, it really, you've got to... The history of migration out of Africa is actually much more complicated than that. You've got to distinguish, in this case, between anatomically modern humans, people who look pretty much like us, and people who act like us, people who are behaviorally modern. And given that our species is kind of created by our brains, we are Homo sapiens, wise man, it's really the behaviorally modern humans that we're interested in. So at 100,000 years ago, you're absolutely right. There are individuals in Africa and shortly thereafter just outside of Africa in the Middle East who look pretty much like us. but they're not acting like us. They haven't gone through the change in behavior which led to something we call the Upper Paleolithic in archaeology, a change in the way we interacted with the world, the creation of art, probably fully modern language like we're speaking now, syntactic language, change in group structure, and so on. That's when we really became modern humans. And so that exodus didn't actually occur until around 50 to 60,000 years ago, we think, from looking at the genetic data. Now, the people who are around at 100,000 years ago, as you said, yes, they did start to leave Africa. They made it into the Middle East, in fact. But after 80,000 years ago, they retreated back into Africa or went extinct. They didn't continue to exist outside of Africa. And in fact, at those sites in the Middle East that they made these initial forays out of Africa into, they were replaced by Neanderthals. And so they're pulling back into Africa after 80,000 years ago, and it's not until after 60,000 years ago that we get the real onslaught of modern humans with this modern human behavior.
Okay, so let's start now at 50,000 years, where humans that behave like us begin to migrate, and then a great diaspora begins to take place. So start to trace for us some of the markers as we trace the lineage of humans.
Well, so around 50 to 60,000 years ago, there was very likely an early migration along the southern coast of Asia. We can trace a lineage defined by a marker we call M130 or RPS4YT. You can call it the coastal marker, though, if you will. And this is a very rapid migration, we believe, that made it to Australia virtually overnight, within a few thousand years probably of leaving Africa. And we can trace the migration of these genetic lineages by looking at the DNA of people living on that route today. So people living in southern India, for instance, retain traces of these migrants who went through 50,000 years ago, an extraordinary thing that these people, in essence, have been living in the same place for 50,000 years and haven't dispersed their genes all over the place. You can still see the palimpsest, a glimpse of this migratory route, which is a good thing, because archaeologically there's no evidence for it. Not until around 30, 35,000 years ago did we see modern human remains and modern human tools in southern India. And yet we see modern human remains in Australia at around 50,000 years ago. So clearly there's a disconnect there. They must have made it through India in order to reach Australia, unless they simply leapt from Africa to Australia, which of course is impossible. So the genetics is really giving us the clues about this very early migration along the coast. We believe there was a second migration very soon after this, maybe 45,000 years ago, which went up into the Middle East. And from there, these people actually became the ones who populated most of the Northern Hemisphere, most of Asia, Europe, and ultimately the Americas.
Okay, now that migration that went north, the second migration, I understand then splits. I understand part going into Asia and part going into Europe. But could you elaborate?
Yeah, absolutely. These people are carrying a marker we call M89. It is, a second out of Africa marker. They trace back to, again, a common origin in Africa. But this is a second wave of migration that, as you say, went up into the Middle East. From there, some of them went over into Europe, but not many, we think, because these kind of ancient lineages that would have been found in the Middle East at that time are not found at very high frequency in Europe. Oddly enough, what they chose to do was to migrate into Central Asia. Now, why did they do this? Probably because as people who were adapted to life on the East African savannas, which is where we believe all of this very early stuff went on, the origin of modern humans and so on, these are grassland dwellers. These people would have wanted to follow the game, the food. And the grasslands lead you into Central Asia out of the Middle East. They don't lead you across Anatolia and into the Balkans. The Balkans are mountainous, forested, etc. And so probably we believe they migrated into Central Asia following the herds. And there's very good genetic evidence for this, because the people who lived in Central Asia later migrated westward into Europe, eastward into East Asia, and ultimately into the Americas.
Okay, so we have the second migration with the M89 marker going north, going into now Central Asia, and then at that point splitting in half, more or less. One group then going into Europe, becoming the Europeans, and the other part going into Asia, becoming the Asians.
Yes.
Okay, now where do the Native Americans now come into play?
Well, the Native Americans come out of this Central Asian cauldron, if you will. I mean, this bubbling cauldron of humanity which spewed out people into Europe and into Asia. Some of them migrated north into Siberia, and around 15,000 years ago or so, certainly no earlier than 20,000 years ago, based on the genetic dates we have, a few of these people went across the Bering Land Bridge, which existed at that time as a result of the last ice age. The sea levels had dropped, and so there was a land connection between Northeast Asia and the northwestern part of North America. They migrated across into Alaska and ultimately down into North America around 15,000 years ago again.
Okay. Now, as I understand, you can actually trace in Native American peoples not just one wave, but actually several waves of early humans that went through Alaska into the Americas. Is that right?
Yeah, this is the earliest wave of migration, and it's the one that made it very rapidly down into South America, and it is the main wave of migration, we believe, simply because it's these markers, the most common ones we see in Native American populations. But there's good evidence that there was a second migration around 6,000 to 8,000 years ago along the coast, because at that time the Bering Land Bridge had been submerged again, the ice sheets had started to retreat. And so the only way that people could have gotten there is by using boats. And in fact, the distribution of the lineages that probably composed that second wave of migration are found in the western part of North America. They're not found in South America. So it's consistent. The genetic pattern is consistent with what we know about the paleoclimatology, the geology, and so on. So this second migration came across into North America, and the people settled along the coast. And then from there, migrated somewhat inland.
Now, there's a controversy going on right now concerning Kennewick Man that you're probably familiar with. We have the remnants of a very ancient remains of an individual that seems to predate many of the other Native American fossils that have been found. And this person may not even resemble the other Native Americans according to facial reconstructions that have been done. But the question is then, who owns these bones? Do Native Americans then, can they bury them as their ancestor? Or do scientists analyze them as nothing but one of several waves that came over from Asia?
Yeah, well, Kennewick is interesting, but actually not anomalous, because all of the skeletons or skulls that I'm aware of dating from around that time. Kennewick is actually a fairly early remain. It dates from around 9,000 years ago. Most of the remains, the skulls that have been recovered from that time period, the kind of 8 to 11,000 year ago period, look more European than today's Native Americans. And it doesn't matter where they're found. They found skulls in Brazil from that time period that also look a little bit more European. Why is this? Were they, Europeans who had migrated across? No, clearly, again, you look at the genetic lineages, and all Native Americans came out of Asia from Siberia. The reason they look perhaps a little bit more European, again, traces back to this origin in Central Asia. Remember, this is the same group of people who gave rise to the Europeans. So it's probably as a result of the shared ancestry with Europeans long ago on the steppes of Central Asia. So that begs the question, why do today's Native Americans not look like that as well? It's possible that this second wave of migration, which we believe came from further east in Asia, could have brought people who looked a little bit more East Asian or Mongoloid in appearance. And perhaps the mixing of these groups changed the appearance of the Native Americans. It's also possible there were local events that people, over time change anyway. You move into a new area, particularly if the population size is small, and your appearance will change. Your gene frequencies will change somewhat due to something we call genetic drift. We don't know exactly, but very clearly the people living in the Americas today, the Native Americans, trace their ancestry back to this part of Asia, and it's not that there were wandering bands of Europeans here before them.
Okay, now let's talk about the Polynesians. Where do the Polynesians fit into this?
The Polynesians are quite interesting. They ultimately trace back, and I talked about this in my book, The Journey of Man. They ultimately trace back to an origin in Southeast Asia. And their expansion into the Pacific was driven by the expansion of rice agriculture in East Asia, which increased the population pressure, and people set out on voyages to find new lands to cultivate and so on. And as they migrated southward down into Indonesia and ultimately out into Melanesia around New Guinea, they began to take longer and longer voyages. And some of them, at some point around 5,000 years ago, 4,000 years ago, set off into the Pacific. And you can literally trace the migration of people from island to island with these genetic markers, but they do trace back to this region of Southeast Asia. And we believe, due to the timing, that it probably was ultimately driven by this expansion, the expanding population as a result of the development of rice agriculture.
Okay. Now we also have genetic mysteries that go back centuries. For example, in northern Japan, we have the Ainu people who are extremely hairy. They're some of the hairiest Caucasians on the planet Earth, from what I understand. They don't look like the native Japanese, who are Asian-looking. And so where did the Ainu of northern Japan come from?
Well, the first point to make is that physical appearance can actually change fairly rapidly. If you take the evidence at face value, everybody living in the world today, share an ancestry in Africa around 50,000 years ago. That's only a couple of thousand generations. That means that within the last couple of thousand generations, we have generated all of the physical diversity we see in the world today. And in fact, even on local levels, you find people changing their appearance today through something we call sexual selection. This was first suggested by Darwin over 100 years ago as the reason why people do look so different. You choose people to mate with on the basis of what you find attractive, and that varies according to where you are in the world. And so, I read a story in the Times of London a couple of years ago about a village in Romania where all of the women have mustaches because the men in that particular region find it very attractive. And, over time this may become a defining feature which distinguishes them from people in the surrounding area. So simply because people look different doesn't mean that they have a very different ancestry from the people living nearby. Now, in the case of the Ainu, there are certain markers that are at higher frequency in the Ainu, and they do correlate with probably an earlier expansion into Japan. So perhaps these were the aboriginal inhabitants. Now, it's likely that these people came out of Asia from ultimately the Central Asian stock. So it is consistent, again, with this origin ultimately in Central Asia, the same one that gave rise to the Europeans. So they're retaining perhaps European features. Maybe that is part of the reason they do look different from the rest of the Japanese.
Okay, so to sum up, we had the first migration out of Africa that followed the coastline into India and into Australia. We had the second migration that carried the M89 marker that went into Central Asia, that then split into many directions, including Europe and China and then the Americas. Were there other migrations out of Africa?
Yeah, there has been a certain amount of genetic exchange across the Sahara, but the Sahara is a pretty formidable barrier. There have been back migrations into Africa from the Middle East within the last 10 to 20,000 years. And, of course, there's exchange going on today, and as people, began to sail ships, thinking about the Polynesian expansion, there was actually a migration of Polynesians westward across the Indian Ocean, settling in Madagascar a couple of thousand years ago. And they speak a language which is related to the Polynesian languages, Malagasy, totally unrelated to the African languages spoken nearby. So, there has been some exchange with sub-Saharan Africa, but not much because of, again, that formidable barrier, the Sahara, which has kept populations apart.
And also, what was the mechanism that drove early humans out of Africa? Was it the changing climate? After all, there was an ice age going on, especially in the northern and southern latitudes. What was the reason why there were all these migrations out of Africa starting around 50, 60,000 years ago?
Well, we do think it comes down to climate change. As you say, we were headed into the worst part of the last ice age, which began roughly 110, 120,000 years ago. But it really started to get bad after around 70,000 years ago. And in fact, we know from looking at other parts of the genome, not the Y chromosome, not mitochondrial DNA, but looking at the autosomal markers, as we call them, that the population size probably crashed around that time as we were going into the worst part of the last ice age. In fact, some of the most recent results coming out of Mark Feldman's group at Stanford suggest that the population dropped down to a couple of thousand individuals. So we're nearly extinct at that time. We're holding on by our fingernails. What we think happened was the ones who survived because they were very clever. They'd gone through what we call the great leap forward in behavior, when we became behaviorally modern. And that adaptation, if you will, that ability to survive in these harsh conditions also gave them what they needed to be able to go out and take over the world. And so once they survive, once they develop these skills, once they go through what is potentially a genetically caused change in brain structure, once they become smart enough, they can then go out and live in places like Siberia, where, the temperatures drop to minus 70 in the winter. And they were living there during the last ice age. They had to have been living there in order to make it into the Americas. Absolutely amazing. We are the only species of hominid that's ever been able to live in those conditions. And it's because we are supremely adaptable culturally, because we've evolved this amazing brain that allows us to do that.
Now, according to the history books, Genghis Khan conquered a huge chunk of the surface of the planet Earth, and some people claim to be their descendants. So the question is, was Genghis Khan really the father of Mongolia?
The search for Genghis, yes. This is work that really came secondarily out of, again, this project to try and map the migration through Asia. And I've spent a lot of time over the last decade working and living in Central Asia, taking samples from a lot of unusual populations. Absolutely fascinating part of the world. And one of the things you hear over and over again from people living there is, we must be related to Genghis Khan. He's like a local, historical figure that everyone wants to have some connection with. And so, it's something that's in the back of your mind as you're doing these genetic studies. We weren't really setting out to find his Y chromosome, though. What happened, though, was as a result of doing this analysis on one of the lineages, we noticed a particular set of related Y chromosomes, what we call haplotypes. There's sets of markers that we study. A particular set of related haplotypes that seemed to be at pretty high frequency, and yet they were very, very closely related. And we said, this is kind of weird. What's the distribution? It turns out that the distribution overlaps almost exactly with the distribution of his empire. So we said, well, that's kind of odd. How old is this? If you see something that's that widespread, remember, this is the largest land empire that's ever existed. Absolutely amazing. If it's that widespread, it should be pretty old. Well, it turns out that it traces back to an origin around 800 years ago, right around the time that Genghis himself was born.
Well, I'm afraid that's it for exploration.
Good day.